All right, this example, this is actually a long example, but let's go ahead and get started. We have a simple vapor power plant operating at steady state. Water is the working fluid. We're given information about the state, at least some of the information about the states at various points in the cycle. We're told to ignore heat transfer and kinetic and potential energy effects, and we're also given the mass flow rate through the system. That mass flow rate through the system, by the way, is this mass flow rate going this way. That's the 109 kilograms per second. So state 1 obviously is here. We're going to go through a turbine, extract some power, then we go through a condenser where some heat is offloaded. That heat is offloaded to some cooling water. I'm going to call the mass flow rate over here m.cw for cooling water. So we have some cooling water that is taking that heat from the cycle and removing it. Then we go to state 3, we go through a pump where we're putting in some power. State 4 into a steam generator. This is like your boiler or evaporator. It's where we're putting in heat. This heat's coming from burning some fuel, for example. And this gives, puts energy into the working fluid, and then we continue the cycle. We're given some information about the states here. We're given pressures, some temperatures. We're told the quality, at least at a couple of locations here. And we're not given all the information, so we're going to have to do some lookup of properties from property tables. We're asked to determine the net power developed from the system, thermal efficiency of the power cycle, the isentropic turbine efficiency and isentropic pump efficiency, the mass flow rate of the cooling water in the condenser, so that's this one, and the rates of entropy production for the turbine, condenser, and the pump. So turbine, condenser, and pump. So there's a lot that we need to do here. The first thing that what we should do is just continue to fill out this table. We know that when we're trying to calculate the net power and the thermal efficiency, all of these things, we're going to need to have specific enthalpies and specific entropies. So we're going to want to fill out this table to find that information. So that's something that you should already be familiar with. It's tedious to do, but it's a necessary part of the problem, and we just have to do it. So I'm not going to dwell on it too much, but I'll fill out the table here for you. So here's the state. We have state 1, state 2, 3, 4, 5, and 6. Pressure, this is in bar absolute. So we're told it's 100, 0.08, 0.08, 100, 1 and 1. Temperatures, these are in degrees Celsius. So 520. So the only place we are, so 520, 43, 20, and 35. So okay, so we're given those temperatures, and then we're also given the qualities. I'm just writing down, just rewriting this table so that we can start filling in some additional information. So let me put in a phase column here. So if you look at state 2, since we're given a quality right here, same with state 3, we know that those are saturated liquid vapor mixtures. So this is SLVM. This one is actually a saturated liquid because the quality is 0. If you look up the first state, that one is in a superheated vapor state when you go to the tables. So all of these things are coming from the property tables for water. Okay, so there's no quality for that. If you look up the value for the specific enthalpy in kilojoules per kilogram, for this it'll be 3426.4. And if you look up the specific entropy, that'll be in kilojoules per kilogram Kelvin. For that state, it's 6.665. Okay, so we're starting to fill in information in this table. The second state, state number 2, we know, again, that it's a saturated liquid vapor mixture because you have a quality. If you look up the saturation temperature corresponding to that pressure, it comes out to be 41.51. That'll be the same saturation temperature as the next state, state 3, because they're both at the same pressure, and this is a saturated liquid vapor mixture, this is a saturated liquid, so they'll have the same saturation temperature. Okay. To find the saturated liquid values, we just use the HF values, right? So here what we're going to do is the H will be the saturated liquid value. Same sort of thing for the specific entropy. It'll be the saturated liquid value from the table. So we can look those up pretty quickly. That's 173.08, 0.59249 for the specific entropy. To find state 2, we have to make use of our expressions for dealing with saturated liquid vapor mixture. So it'll look like this for the specific enthalpy. So this would be like it's H2. Oops. And then we have the expression for the specific entropy. It looks essentially the same. Okay, so we can look up the values for that, plug in the numbers, and so this specific enthalpy is 2335.96, specific entropy 7.46382. All right. Now the next three entries in the table, if you look up those in the table, or look up those in the property tables, what you'll find that is that all three of those are compressed liquids. So these are all compressed liquids for those conditions. So again, the quality is not applicable, doesn't make any sense for those. To find the specific enthalpy, we'll make use of the compressed liquid expressions. Remember, for the compressed liquid at some temperature, the specific enthalpy for compressed liquid at some temperature and pressure is about equal to the specific enthalpy at the saturated liquid state at the same temperature, plus the pressure minus the saturation pressure at that same temperature, times the specific volume for the saturated liquid state at that same temperature. So that's how you would find those. And the specific entropy for compressed liquid is about equal to the specific entropy for the saturated liquid at the same temperature. So that's how you'll find the properties for the compressed liquid states. So if you work out those numbers, state 4 specific enthalpy is 190.152, specific enthalpy for state 5 is 86.199, specific enthalpy for state 6 is 146.725. Same thing for specific entropies. I'm not going to read the numbers because you didn't pay all your tuition just to hear me read off a bunch of numbers. Okay, so you can just look on the screen and see them. Okay, so the very first part of this problem is just figuring out all of these properties because we're going to make use of them in just a little bit. And it's you just need to have them. It's tedious, like I said, but a necessary part of the problem, so we just have to have them. Okay, let's go back up to the problem statement to see what we have to do with those properties. So the first one is to find the net power developed by the system. So that means what we're going to do is we're going to have to find the power coming out of the turbine and the power going into the pump. So that means I'm going to apply the first law to a control volume surrounding the turbine, and then separately I'll do the first law to a control volume surrounding the pump. So let me write it out for the turbine. First law for the turbine. So we can write out, I'll just do it this first time, but I'll write out the full first law expression. Okay, so there's our first law. We said that the cycle is at steady state, so the left-hand side is 0. We're going to neglect kinetic and potential energy changes because we were told to do that, and they're typically pretty small anyway. We'll assume that the turbine is operating adiabatically, so we'll neglect that, and we know from conservation of mass, I'll just write that over here. We know that, again, it's steady state. There's one inlet and one outlet, so m dot in equals m dot out, which equals m dot. Okay, so the power out of that turbine will be m dot times, let's go back and see where, coming in is state 1, coming into the turbine state 1 and going out is state 2. So this will be H1 minus H2. Okay, so, and if you plug in the numbers for that, it comes out to be 118.86 megawatts. It's a big number. It's because the mass flow rate is a large number. So that's the power we get out of the turbine. If we apply the first law for the pump in the same, everything looks the same in the first law expression. I'm not going to write it all out. What you'll get there is the power going in will be m dot, this one comes out to be m dot H4 minus H3. So that's the power going into the pump. And when you plug those numbers in, it's a much smaller number. It comes out to be 1.86 megawatts. So then if you want the net power out, that'll be W dot out minus W dot in. And then when you plug those numbers in, it comes out to be 117.00 megawatts. So just 117 megawatts. I think we were just asked to find the net power. Okay, so that's part A. Find 117 megawatts. Let's go back up to the problem statement. We're asked to find the thermal efficiency of this power cycle. So the thermal efficiency, if you recall, for a power cycle, it looks like the following. Thermal efficiency for a power cycle is the net power you get out of the cycle divided by the heat transfer you have to put in, the amount of heat you have to put in. So this is being applied to a control volume that surrounds the whole cycle here. Okay, so we just calculated the net power out. Now we need to find the rate at which we're putting heat transfer in. So that's going to occur over here in the steam generator. So let's draw another control volume around that. And then we'll apply the first law to that steam generator so we can find Q dot in. Okay, so the first law for the steam generator. I'm not going to work out the first law. Let me just go back up to the picture here. It's still going to be steady state. So I'm not going to do all the details. I'm just going to kind of go from this equation up here. So it's first term on the left-hand side, time rate of change of total energy in the control volume. That's 0 because it's steady state. We're again neglecting kinetic and potential energy effects. For a steam generator, the power out is 0 because it's a passive device. So that term is 0. Q dot in, of course, we leave in because there is some heat transfer. The steam generator is not adiabatic. There's some heat transfer occurring there. So when you work out the first law for this, this particular term comes out to be Q dot in is equal to m dot times H1 minus H2. And then when you plug the numbers in for that, the Q dot in is 352.75 megawatts. Right? So then if we want to find the thermal efficiency of the cycle, I'll just repeat it here. It's the net power out divided by the heat that you have to put in. It's not the net heat you put in, it's just how much heat you put in. Because that's what's costing us money, is how much heat we're having to put in. So this would be 117 megawatts all over 352.75 megawatts. And when you work out the numbers, it's about 33%. It's 0.332, 33.2%. So that's our thermal efficiency for this entire cycle. So that was part B. Let's go back up to the problem statement. So we've done parts A and B. Now let's look at part C, the isentropic turbine efficiency. And then part D will be very similar, the isentropic pump efficiency. So for that, let's just go back to our definition for the isentropic turbine efficiency. That'll be the actual power you get out of the turbine divided by the power you would get out of the turbine if it was isentropic operation. And when you apply the first law, we already did this for, just go back up here, we already did it for the turbine. It was right here, it was H1 minus H2. So this will be, the m dots will divide through. You'll just get H1 minus H2 on the top, and then on the bottom it'll be H1 minus H2S. The 2S indicating that that's the specific enthalpy if the flow through the turbine was isentropic. Okay. So we already know the values for H1 and H2. Those are given in the table. So all we need to do is find the specific enthalpy for the isentropic case. So for the isentropic case, we know that the pressure, P2S, will still be the same as P2. It's operating between the same pressures. So that's 0.08 bar, absolute. And we also know for the isentropic case, S2S will be equal to S1, which from the table is 6.665 kilojoules per kilogram Kelvin. We looked that up in the table, right? So, so those are our two properties. From that, we can go back to the property tables to see what the specific enthalpy will be. And what you'll find is that we're in a saturated liquid vapor mixture phase, so we have to calculate the quality and then calculate the specific enthalpy. So let me just do that. The quality will look like the following. For this isentropic case, it'll be S2S, which we know, 6.665, minus SF, saturated vapor, oops, there we go, SF at 2S, SG at 2S minus SF at 2S. So we would need to look up, so that the SF2S, this is the saturated liquid specific entropy. SG2S, that's the saturated vapor specific entropy. Those you can find because we know we're dealing with a pressure of 0.08 bar saturated liquid vapor mixture. So that's where those values come from. When you work out the numbers, S2S comes out to be about 79%, 0.79537. And then from there, we can calculate H2S. H2S will just be 1 minus the quality at 2S times HF 2S, and then you've done this sort of thing before, so this shouldn't be surprising. When you work out the numbers for this, it comes out to be 2084.61 kilojoules per kilogram. All right, so now that we have that value for H2S, we know H1 and H2 from the table. We now know H2S. We can plug in the numbers, and what we get is the isentropic turbine efficiency comes out to be 0.813 or 81.3%. Okay, so it's not operating as efficiently as it could be, right? It's there's room for improvement. We can do the same sort of thing to find isentropic efficiency for the pump. For the pump, what we'll have is the power that you have to put in under the isentropic conditions divided by the actual power in. That's the isentropic pump efficiency. And the reason it's written this way is because the work or the power you have to put in under isentropic conditions will be less than the actual power that you have to put in, so that ratio is less than 1. And we already did the first law for the pump. That was up here, H4 minus H3. So we can write this out as H4, fix that, H4 minus H3 in the denominator. In the numerator, it will be H4S minus H3. We know the values for H4 and H3 from the property tables. We already calculated those or evaluated those. H4S we still need to find. For that, we again can go back to knowing the pressure at 4S. That'll be the same pressure at 4 because we're still operating between the same pressures. That would be 100 bar, if you go back to the picture and look at it. And then we also know S4S is equal to S3 because it's isentropic. So that's 0.59249 kilojoules per kilogram Kelvin. If you look in the tables, this will be in a compressed liquid phase. And then you can go kind of through the same procedure that I went through before for the turbine. You know, you're just trying to evaluate the properties. And what you'll get when all is said and done is H4S is 183.92 kilojoules per kilogram. You have to, when evaluating this, you have to make use of the compressed liquid approximation. Recall that compressed liquid looks like this. Oops, I should be more careful. Actually, I won't even write it down. Let me just go back up. I wrote it down up here. You have to make use of these compressed liquid approximations, right this expression here. So you'd have to use that to find H4S because it's a compressed liquid. For more details, I have the printout of the solution. You can look at that part. When you plug in the numbers to find the pump isentropic efficiency, now that we have everything, it comes out to be 0.635 or 63.5%. It's lower than that for the turbine, and that's pretty typical. As I've mentioned in a previous lecture, that turbine efficiencies tend to be higher than pump efficiencies because of the way the viscous losses occur in turbines and pumps is a little bit different. All right, let's go on to the next part of the problem. So now what we've done is parts A through D. We've done A through D. Now what we're trying to do is find the mass flow rate of the cooling water in the condenser. So we want to find this m dot CW. For that, what we'll do is we'll make use of the first law applied to the condenser. And the reason for that is because I know, the reason I think that is because I know the conditions from states 2 to 3, right? I know the specific enthalpies for that. So I'm thinking about the first law. So I would know those specific enthalpies, and I also know that mass flow rate. For states 5 and 6, I also know those specific enthalpies down in the table here. The only thing I'm missing is the mass flow rate. So really I'm just exchanging some energy between the cycle flow and the cooling water flow. So I'm going to apply the first law between those. So first law applied to the condenser. Let me go back up to my expression for the first law that we started with way up here. So we'll still have the same first law expression. It'll still be steady state, so the left-hand side is 0. There's no heat transfer out of the across this control volume. Let me go back up to the picture. There's no heat transfer across this control volume. On the inside, there's certainly heat transfer between the working fluid in the cycle and then the cooling water. There's definitely heat transfer occurring inside, but there's no heat transfer crossing that boundary. So our Q dot term will be 0. The W dot will be 0 because it's a passive device. We'll still neglect kinetic and potential energies. The only thing really different here is that there are 2 mass flow rates coming in and 2 mass flow rates going out. So what we'll have from the first law, left-hand side is 0. We'll have the mass flow rate coming in of just through the cycle times its specific enthalpy, and that one is H2. And then we have the mass flow rate of the cooling water coming in times its specific enthalpy. That'll be H5. And then going out through the cycle, it'll be m dot times H3. And going out through the cooling water, it'll be m dot CW times H6. So we can rearrange this to solve for the cooling water mass flow rate. And if you do that, it'll be m dot times H2 minus H3 all over H6 minus H5. So this comes from a first law analysis. We've calculated all of these, or we've evaluated all of those specific enthalpies, and we're given the mass flow rate coming in, so we can find the mass flow rate of the cooling water, and it comes out to be a big number, 3,900 kilograms per second. A lot of cooling water there. So there is that part of the problem. So we've now done part E, just an application of the first law. Lastly, for part F, find the rates of entropy production for the turbine, condenser, and pump. Well, this will be an entropy equation problem, and we'll apply the entropy equation to the turbine, the pump, and the condenser. Those are the three that we're asked to find. So we'll just apply the entropy equation to all three of those. Okay, so let me write out the entropy equation in its full form. Okay, so there's the entropy equation. Again, the left-hand side is going to be 0 because it's steady state. There is no heat transfer in any of those devices. They're all adiabatic, so that term is 0. There's only one inlet and one outlet for at least the pump and the turbine. So for the pump, it'll look like this. Sigma dot will be m dot times S out minus S in. So for that one, it'll be S4 minus S3. For the turbine, the sigma dot will be m dot times S out. That one will be, the S out should be S2 minus S1. And then for the condenser, that one's a little more complicated because we have 2 inlets and 2 outlets. So S dot for the condenser should be m dot times this m dot times let's see, S3 minus S2. So that's kind of out minus in for the cycle, and then we have to add in the same the entropy flux for the cooling water. That'll be S6 minus S5. And the reason, again, you have 2 of these is because you have flow coming in and out from the cycle and flow coming in and out from the cooling water. So when you plug in plug in the values for these, we know what m dot is. That's given. We looked up all the values for the specific entropies and put those in the table. We just solved for the mass flow rate of the cooling water. So when you work out the numbers for the pump, it's 2.1538 kilowatts per Kelvin. For the turbine, it's 87.071 kilowatts per Kelvin. And for the condenser, it's 63.735 kilowatts per Kelvin. So you can see that the turbine has the greatest amount of irreversibility, and the condenser has, the pump has by far the smallest amount of irreversibility. So if you were going to focus on a way to make this cycle more thermally efficient, the place that you would focus your efforts would really be mostly on the turbine and condenser. You wouldn't worry so much about the pump because it adds very little irreversibility. So to increase the thermal efficiency of the cycle, really focus your energies on trying to improve the conditions across the turbine. That would be where you would have your most bang for your buck. All right, that does it for this example. This one is very comprehensive. It covers a lot of different things. We're dealing with the cycle, first law, the entropy equation, isentropic efficiencies, and property lookups. So it's taking a lot of what you've done in this whole course and putting it all into one problem. All right, we'll go ahead and end it there.